Imagine this. There's an annual Lego conference that is going to happen in the town. You have 5,000 excited Legos that are going to come in. There's a master Lego who's going to give a keynote speech. Before the day of the event, there was a dry run. And in the dry run, there were only 1,000 users that were called in. When these users started coming in to the auditorium, they started running into some issues with the wireless. To troubleshoot this, a network engineer was called in, and his name is Rivi. So Rivi is a wireless engineer. He knows how to troubleshoot the network, and he's going to need help from you and me. The first thing Rivi saw was the channel utilization in the network. To his amazement, he saw that 6 GHz band is not even enabled and was not even considered. And there were only 2 radios that were enabled, which were 2.4 and 5 GHz. He knows that on 2.4 there are only 3 non-overlapping channels that are available, whereas on 5 GHz there are 25 non-overlapping channels that are available. The first thing he did was enable band steering. So what is band steering? So band steering is a mechanism where you push the clients from 2.4 to 5 GHz. So now he started looking at 5 GHz channel, and he saw, even though it says that there are 25 non-overlapping channels, a few of these channels are blocked by Doppler weather radar. There is one channel which is 165 which can't be used, and then there are other bands which are unit 2 and unit 2E. They are affected by DFS and are used by radars, satellites and weather stations. Even though there was no radar which was detected in the network, still the channel utilization was pretty high. Now looking further, he saw that there is something called as channel bonding which is enabled. Now what is channel bonding? If you go back to the same figure, it is basically when we combine two channels together, let's say in this case channel 36 or 40 together, it becomes one single band. And here you end up having one channel, let's say channel 36. Now, to give an example, if you combine two channels, let's say 52 and 56 together, you will end up having one channel, which is channel 52. Right? Now, how exactly channel bonding was working before? So when these users were back at their desk, they were not running into the same issue. In the enterprise environment, you can have channel bonding enabled if the number of access points are less. When you enable channel bonding, let's say you had 21 free channels that were available. If you enable 40 megahertz, you just divide it by 2. And you end up having only 10 free channels in the network. Why channel reuse is a problem? So let's say you have all these access points in the network. One was on channel 36, 44, 52, 60, 44. These are considering 40 megahertz wide channel width. Now, if you see closely, there are 2 access points that are on channel 149. If there is a client which is on channel 149 and it is able to hear the other access point which is adjacent and also on channel 149, all the client devices that are connected with these 2 APs have to wait for the medium to get free, and then they have to contend for the medium. There is a process of CSMAC that is followed in the network, which is collision avoidance protocol. So wireless is a medium which is half duplex in nature, and it's a medium which is also called as listen before talk. A channel is nothing but set of frequencies that are available for a client device to transmit or receive. If there are 2 access points that are close to each other and they are transmitting on the same channel, all the other devices connected to these APs have to wait until the medium is free. And what it does, it basically increases the co-channel interference. So in our auditorium scenario, because we have 5,000 users and we would be needing approximately 30 access points, what happens is the channel reuse goes high, and the same channel is reused by multiple APs. So the best way forward was to disable 40 megahertz and have 20 megahertz wide channel only for auditorium. After making this change, Rivi saw a considerable improvement. Congratulations to you and Rivi in troubleshooting this. Rivi knows that even though I'm getting a very good signal, still the SNR is not acceptable. So what is an SNR? SNR is signal to noise ratio. When you receive signal on your phone, it is called as RSSI, which is receive signal strength indicator. And what is SNR? It is RSSI minus the noise in your network. So what is noise? Let's say there is a classroom and everyone is talking at the same time and there is a bell that is ringing, right? Everything is a noise at the time. In wireless, noise can be of two types. It can be 802.11 or non-802.11 noise. So some examples of 802.11 noise are co-channel interference that we just discussed. Then it can be adjacent channel interference, where there are two different APs on the adjacent channel, let's say channel 36, and then we have an AP on channel 40, right? So you'll say that, Saurabh, you just told us that these APs will not interfere with each other and it's a good thing. Well, they don't interfere on the major lobe, but there are side lobes also. In this diagram right here on 2.4 gigahertz channel, you see right here this green thing. This is your major lobe, but then it is not like just one lobe. There are smaller lobes as well. And that is where your adjacent channel interference comes into play. So how you can avoid it? There is transmit power on your access points. You don't need to have your APs blasting at the highest power. You can reduce the transmit power and then reduce the cell size that we will discuss later in the video. Then there is a hidden node issue that can be faced in the network. Let's say you have a big auditorium right here. You have all the access points. There is one device right outside. Now, this device is on the same channel and it is transmitting. Now you don't know where exactly it is. This device is not able to hear you, but these APs have a very good receiving aperture and they are able to hear this small device which is outside of your auditorium. And because this is on the same channel, these guys wait before transmitting and it basically blocks the network, some tears. Alright, so moving on, you can also have rogue access points in the network, which are basically the APs. Either they can be from your same network or they can be from your adjacent building, which are not controlled by you. Right? So the best way, let's say if there is an AP in your network, you can do a post-deployment survey to find out. You can also look at your wireless controllers which manage the access point. Usually they show that, okay, there is a rogue access point that is detected. The second is the non-802.11 kind of noise. It can be your wireless cameras, ovens, some lighting solutions also have been seen causing the issue. It can be jammers as well. Now, Rivi saw with his spectrum analyzer that there is one Wi-Fi light that is causing some issue and it's blocking the whole medium. So what Rivi did, disabled that light put it on to one particular channel and just blocked that channel from the whole band. So it's a good thing that Rivi had the spectrum analyzer. Now Rivi knew that, okay, if there is a light that can cause this kind of an issue, it can very well be something in the design that can cause issues in the network. He looked up and he saw that there are omnidirectional access points that have been deployed at a height of 40 feet. It was a red flag for Rivi because Rivi knows that omnidirectional antennas, they work well in an enterprise environment, but in an auditorium they are a red flag. So to understand this more, we'll have a look further. Omnidirectional antennas, as you can see here, right? So let's say if you mount it on a ceiling, they have a very big cell size. And what we know that in an auditorium, you should have a smaller cell size because you are not designing for coverage. You have highly dense deployment. Here you have to design for capacity. You want to get a more number of users per access point, right? You don't want 100 users to listen to you. You just want 30 users to listen to you. So for this particular purpose, he knows that he has to use a directional antenna. The wrong AP selection that was done was catastrophic. He knew that he had to get rid of omnis. He has to ditch the omnis. He needs to bring in the directional antennas. Why exactly directional antennas? Let's go back. And where exactly you would mount them. Now, you can see this heat map right here. On the left of the ceiling mount, right here, you'll see that this AP, what you can see, this is an omnidirectional antenna. It's an omnidirectional access point. And here you have a directional AP. And on your right, you have a wall mount. So the same access point on the left is your omni. This right here is omni. And this AP is again directional. Let's say if I give you an auditorium, let's consider this is the auditorium. This is where the speaker is going to be. These are all your sitting areas. Everywhere is your sitting area right here. And you have to do a bad design first. You have omnidirectional APs everywhere. And all these APs are ceiling mount, some are wall mount, whatnot. If you look closely, how is the cell size of every AP? It is huge. It is kind of like you are trying to hold a big pumpkin. It's that kind of a design everywhere, right? So what will happen? Even though you have deployed 20 megahertz, you will still end up having a high adjacent channel interference and a very big overlapping area right here between the two access points. It is going to raise your noise floor. So the best thing here would be to basically take the same auditorium in the corners, place your directional APs. So directional APs have a particular sector that they cover, right? Because you are now designing for capacity. Okay, I have to target specific seating. And let's say if you have to target this middle area right here, your directional AP usually it's able to reach. But let's say if there is any region where directional AP does not reach and you're not able to reach that section, you can always place directional APs on the ceiling. And now you can consider the same figure that we saw earlier. Now this directional AP has a very good antenna pattern, and this directional AP which is on the ceiling, it again has a good antenna pattern, and that is where you are going to ditch the coverage for the capacity. One thing that has to be avoided is the looking good syndrome, where you do not place the APs behind any ceiling. So if you place any access point behind a ceiling, it increases the multipath distortion. Your antenna propagation, it just keeps on reflecting, and whatever signal comes out, it is an attenuated signal, because this thing right here, which is probably your ceiling or some metal ducts, they usually attenuate the signals. So putting it all together, what all you have to do is ditch the omnidirectional antennas, use directional wherever you can, shrink the lanes, use 20 megahertz channel width, do not use 40 megahertz on 5 gigahertz. If you have an option, always enable 6 gigahertz. It comes with some caveats with newer security protocols, and you can always use 40 megahertz on this band. It's a very wide band. Kill the aesthetics. Do not place APs behind the ceilings. Do not paint them. Turn down the TX power on the access points. Do not have them blasting on very high power or maximum power. Reduce the cell size. Reduce the adjacent channel, core channel interference in your network. Disable the lower data rates. Lower data rate is basically when you move away from the access point, your data rates decrease and you're not able to transmit effectively. So disable those lower data rates. Let your client devices connect to the closest access points. Always have a look and audit your access points. Always audit your APs and always audit your APs and check whether they are able to negotiate maximum power. If an AP is not getting correct power, they will not be able to work at peak performance. Always consider capacity over coverage in auditorium scenarios or in high density scenarios. And the last point, if you have already deployed Wi-Fi 6, 6E or Wi-Fi 7 access points, there are major improvements in the wireless standard where you have protocol level improvements which supports multi-user MIMO, and you have OFDMAs, and you have BSS coloring, MLO, all these standards helping you achieve high performance. So after doing all these things, there was a considerable improvement, and then on the day of the event, things were fine. It was a spectacular performance by Master Lego in delivering the speech, and everyone was really happy. Kudos to you and Rivi in troubleshooting this network.